up and running. Okay, welcome back. Hopefully Friday is like an afternoon to recharge a little bit. Now jump back in with that time to reflect on what was all this about. This is the last quiz that we'll make for the course. And then when we get back from Thanksgiving, Monday, Wednesday, Friday is just working on independent projects. So like identifying some kind of problem, building some kind of equation of motion or a model, like physics model, and then figuring out a way to say what those results mean. So the quizzes that we've been building together is kind of like the same thing that we're doing for that final project. It's just that it's, instead of as a group coming up with something, it's individual. Everybody comes up with their own version. So we got one more practice round, and then we'll put it into practice. Practice 4 into practice. So what was module 4 about? What were we doing? What happened? Yeah. Energy, yep. What made up energy? Like what was what was energy? Like the buzz, we were just like energized, like lots of Red Bull, super excited to be here. Or like what's the specific like engineering equations? Yeah. Like kinetic energy. We had kinetic energy. So this could be like KE. And again, I called it T. If you want to call it something else, you can do that. So we had some kind of like translational and rotational kind of kinetic energy. What other kind of energy did we have?
We have potential, like gravity and spring.
Yep, yeah. Potential energy. Could have anything where the force only depends on like position. So springs, gravity, even electrostatic and magnetic is all potential energy things, because if you're in a different part of the magnetic field and you move to some other part, the force that was acting on you is always just a function of your position. Yeah, all sorts of stuff. And was that it? Do you only ever have kinetic potential energy? Yeah.
Those are non-conservative forces.
Yeah, so any kind of like non-conservative force, so things that depend on your path, like how far you traveled, or if it depends on your velocity, like how fast you're moving. So drag, friction, what else am I thinking of? Damping, that's the one, damping. So integrating that force over distance, kind of like that. And overall, we had like the main thing that kind of defines dynamics, like thermodynamics of dynamics, is that kinetic potential plus whatever work is put into the system is all going to turn into kinetic and potential. That's like the big energy equation here. Do we do anything else? Yeah.
We had an impulse momentum.
Impulse momentum, yeah. I'll write it out. Where whatever force applied through a certain amount of time changes that momentum vector. And here, the big thing, at least the thing that I think is a really helpful diagram, is kind of, we had some mz0 plus some kind of f delta t is all equal to some new mv final. And probably if you did like intro physics, if you remember those kind of momentum diagrams, it was drawing same kind of vectors, but usually assuming that that f delta t was all zero, just conservation of momentum. But this one's a nice way. You can either show that f delta t is zero, or if it's not zero, you can actually figure out how big that impulse was. Good place to start. Like come up with something to demonstrate, yes, I understand these methods of impulse, momentum, work and energy kind of applications. I guess I should write that, work energy, right? Impulse, momentum, work and energy. So we want to come up with a problem or two problems or a set of like conceptual ideas that would demonstrate that we understand work and energy, impulse, momentum. Good. Thank you. So like as you're kind of thinking out and putting some thoughts down onto a note card or any kind of just putting things down on paper, one of the benefits of using like work energy and impulse momentum is that it's like a pre-integrated form of our equation of motion. So module 3 was, the only point of module 3 was, how do I take these force vectors and turn them into an equation of motion, some kind of second order differential equation. With work and energy, we always end up with velocity is a function of position. Like we always end up with some kind of function like that. And in this one, we always end up with velocity is some function of like a small change in time. So if you're, and again, like if you're problem solving and kind of thinking about things, the other thing that impulse is really good for is when something big happens instantly. When like it would look like infinite acceleration for a very small period of time, it's better to just describe it as a change in momentum. When something bounces off the wall didn't accelerate the ball to infinite acceleration for a tenth of a second. It bounced. It just hit the wall. It was moving 1 meter per second that way. Now it's moving 3/4 of a meter per second in the opposite way. Can't see that. Yeah. Oh yeah. Well, we could look at like pieces of it. Yeah. Okay. Yeah. Yeah. Okay. Does that apply to anything else, or is it always a normal rolling on ramp? Yeah. Anything rolling? Okay. My first thought happened that was like Indiana Jones boulder. Yep. Yeah. Yeah, where we were looking at same question comes up with highway barriers. Sometimes you do want to stop the car, then cause damage outside the highway. So they won't instantly stop it. Yeah. Yeah, me too. They're kind of transferring, you're using the spring. You need the spring to have enough energy to give it an impulse of something. There's some value where if the impulse is this high with wires, and if it's any lower than that, it's not a, you got it. Yeah, that's what this is. The goal is to develop practice work on together. Which one is it? This one. There is, yeah, pretty famous. Yeah. We want to anchor it. Yeah, I think that would work. Depends how big the board was. Yeah, yeah. Something like that. Or we were talking about the rubber family also. Put it around the iceberg? Maybe around the boat. Around the boat, yeah. No. Not the iceberg. Yeah. Yeah. Similar idea, like how do you protect the cargo from or whatever, let's say whatever you're trying to keep safe, there's built something, stop it. I don't know. That's a good question. Like, could you? I don't know if an anchor can bring a boat to a stop. Maybe. It might be able to. Oh yeah. Oh yeah, similar to like when we're trying to sell that tank. Yeah. Yeah, because like math wise, it doesn't matter. It's a spaceship. The land is fire. Yeah. Oh, okay. Yeah. Yeah. How about trying to get like a smooth hill? Okay. I guess I'm looking at this diagram. It looks like similar, but instead of saying that there's a ramp on the cable, it kind of smooth transition from the ramp to yeah. How would that change? Like, the time like that's something you do well. Yeah. I would think so. Yeah. I would agree. We don't have like we spent time trying to figure out these kids the table. We lost all that getting momentum. The only thing that was smooth should not acting in the direction. Momentum conserves or is change. So some things that I saw kind of coming up a couple of times were people thinking about like a ball rolling down that ramp, hitting the table, and then some variations like, okay, well, what if it was, oops, oh, don't need that one, different class. What if it was, instead of like two flat surfaces, what if we had a smoother transition, right? Those kind of questions. But those were two main themes that I saw kind of coming up. Anything else that you were thinking about? I guess the other thing that we didn't really talk about was like angular momentum. Maybe that one is just sort of like, we know it exists, we did it, we'll get back to it. Future work. I didn't see anybody come up with like, well, if I have a planet and another one orbiting, let me calculate the angular momentum based on its position and mass times velocity. Or like, what's the difference between conical orbits versus geostationary orbits? Not today. Did anything, what else was coming up as you were, so ships and rolling balls, or does this apply to anything else, or can we only do a ship or a rolling marble? Does it work for anything else? Because like cargo ship and spaceship, we use same equations, that mv equals f delta t. And it didn't matter whether we were in deep space or in the Chesapeake Bay, both same equation. Where else could it like step back and say like, oh, we could do this for, I don't know, more, less, more specific, less specific, yeah.
I thought of like a fighter jet landing on an aircraft carrier, and they have to like stop it from going off.
Yeah. Have you seen the mechanism, the brakes that they use? It's crazy. Yeah. So we have like fighter jet coming in for a landing, and they can only build the aircraft carrier so large. Actually, one of the main limits to like boats in the Navy is how big the Panama Canal is. Like, can you get through the Panama Canal? That's like one of our limiting factors to like the whole size of the boat. Because I mean, ideally, we could just build a huge LaGuardia on a giant airport and just have it floating out to sea, and then we have no problems with landing planes on it. But then what do you do with it now? Where do you park it? Especially around Yukon, you're never gonna find parking. But here, same thing. We have MV, it's coming in for a landing. We have so many feet of runway, right? So now do we need to figure out, like, we could do like impulse problem, we could do like some kind of force, like what is either average force applied, or I think this one actually uses like tension in a cord. So I think it's almost like it's by time it hits the runway, it's like a mass on a spring. Like, and the spring, the further the jet goes, the more that spring is pulling it back to the center. Yeah. Cool. Yeah. Anything else come up? Something different? I'll let it sink for a second, or float. Let the ideas float, because it's all about boats and ships, floating things, want them up in the air. Oh man, yeah. So like figuring out like how big of a crumple zone you want to protect people inside. Yeah. Okay. Yeah. Oh yeah. Yeah, so you get a potential energy. Yeah. Yeah. Yes, you have to figure out how fast that strike is, and then know the coefficient of restitution of the strike of the ball. How fast ball. Yeah. Alright, so we're seeing through the matrix, seeing like the bigger picture. Alright, so other things that came up were at least and these are crash test dummies in here. But like as a car for safety, there's a section of the car that's designed to kind of crumple and absorb energy. The more you crumple it, the more force it takes to crumple. So it is kind of like a spring. But we could kind of ask these two questions of like passenger like a lot of times it's measured in G's, like how many units of 9.81 meters per second. So 1 G is 9.81 meters per second squared. So if we're trying to keep the passenger always less than 2 G's, then what is the stiffness and how much crumpling could we have as it like strikes that wall, so that the person inside is never coming to an immediate stop. Worst case is like an actual rigid body car striking the wall, and the passenger either goes through the windshield, like continues at the speed of the car, or comes to an immediate stop where acceleration is infinite. Something like that. And well, I say passenger, the crash test dummy, because we want all of this to be done on things that are safe to crash, not actual crashes, so that the actual crash is a non-event. And then, oh my god, what were we just talking about? What were we just talking about? I lost it. Oh, the pinball. So with like a pinball striker, as you pull the thing back and release it, you have the striker itself is always related. Oh my god, whole nother. Like its kinetic energy is potential energy. So the more I pull it back, the faster it's going to go. But when it hits the pinball, now we have an impulse problem where the striker had MV, and now the pinball, we want it to move at some other MV something else. We have like V2 of the striker after it hit the ball and V of the ball, something like that. That one's kind of cool to figure out.
So we're seeing, I don't know, where do we see, how are we doing on time?
Yeah, we got time. What are we ready for? And what do we want to do? It's quiet. We're days away from Thanksgiving. We'll make it there. We're gonna get there. Pretty close. What do you think? What are we ready for? Ready. I know you're ready. Landing jet. Looking at like crashing probably crashing body. Okay. You like Titanic? Stopping Titanic. Yeah. Yeah. Oh, really? Sounds like a two-step process. Momentum, impulse, yeah. So yeah. Ready, like everything looks like you're ready for everything. Every question. Just one, yeah. Block sliding. Okay. Conservative forces.
Feel like friction.
Okay. Yeah.
But I mean,
Okay. Yeah. Yeah, so you could say, no. So in terms of, all right, so let's take a look at this one. Seems like it's starting to ring. And we're here in Connecticut. We're like big aerospace kind of place. We do a lot of this stuff. So kind of the design questions. At least when I look at a problem like this, what are the things that I know versus the things that I can control and things that I can't control. So one thing that I can't control is that once I know the length of the runway, that's done. That's fixed. And that is my delta x. So that's all I have to work with. So that one's a fixed value. The mass and speed of the plane, also a fixed thing. I can't just tell the Navy that, oh, it'll be a lot easier to land if your planes are 10% of the weight that they currently are, just because there's a lot less momentum. Like, what are you talking about? Get out of here. Just tell us how to land the plane. So this one's also, so that one's kind of fixed. This one's kind of my fixed. Like, as far as like, is it something I can play with, or is it a fixed parameter that I need to deal with? But this stiffness, that can be whatever I want it to be. I could have something really stiff and bring it to a stop immediately. Again, sending the pilot through the windshield, because if he's doing 300 miles an hour and then comes to an immediate stop, he's still doing 300 miles an hour. The seatbelt is, now has like seatbelt marks all over him. So I can play around with that kind of K value. So I know initially, so mv equals that f delta t, and then I also know that 1/2 mv squared equals 1/2 k, I can call it like L squared. If I say that it's unstretched when it first lands and then it's fully stretched as it moves on, something like that. So I've got like two equations to work with, and these like two parameters that I can play around with, where like A of the pilot, or at least the average A, is mv over delta t. Or, I mean, really, it's like just v over delta t, right? Because that's the average change in velocity. So I would want that to be less than a certain value. Probably during landing, I don't want the pilot to go through like 3 Gs of force, because there's just no reason to. So maybe I want to keep this like less than 0.5, like half a G, something like you're hitting the brakes pretty hard, but not like, upchucking breakfast during the process. So that would give me a limit on like how much force I would have and how much that A could be. So V squared is that thing, something like that. I'm not like, really I should be going through a few of the steps, but just like identifying main parameters here. Like, so maybe my question would be, what is, I guess I would want to solve for K then, huh? So K would be something like that, at least as a first step. And then check to make sure that my pilot is not having like 3 Gs of acceleration for that K value. So solve for K, plug it into my impulse momentum, and figure out what was that average, stop, something like that. Yeah. I guess that F is really that KX, right? KX delta T, like that. What do we think? Something like that. We've got like spring, getting springs in there, using impulse momentum, like changes in momentum talked about. What is the passage you're feeling in the process? What are other thoughts, ideas, issues? You know, it's the week before Thanksgiving. I'm trying not to keep us over time. Like I haven't done it too many times, just a couple. Nothing? No. Maybe have the jet stop the Titanic. It was going. The jet was landing and reverse the speed of the Titanic.
You can say the jet land on.
Yeah, to bring it to a stop, right? Because if Titanic applies F to jet, jet applies F to Titanic. So it stops it from moving forward. There was like do you ever read like XKCD What If? That's a lot of these kind of questions, but just like more ridiculous. And I think one of them was like, how many BBs would it take to stop a train? Like if you're shooting a BB gun at a moving train, and it would have to be this like rapid fire, like, because sooner or later it'll work, right? Like if you have enough momentum pinging off of a train, each time it hits it, it'll slow down a little bit. But anyway, okay, that's all I have for today. If you're interested and free, the senior design poster presentation is going on right now for mechanical engineers over in Engineering 2. It might be a nice like preview as you're as you're moving towards senior year and those kind of projects. Thanks.